Okay, here's some instructions on how to use the PHeT simulation for the isotopes and atomic mass. So from your D2L content section, you'll recognize when you get to this, but I'm just going to scroll down here and you're going to come to a section, complete the following PHeT simulation for isotopes and atomic mass. This is content 2. Just scroll up just so that the dating techniques, activity 2, and I ask you to make some notes and then go into just practicing what these isotopes really truly mean. You really want to visualize that, have a really good picture of that, and um, it'll just help you better understand the whole dating thing. Okay, so isotopes and atomic mass, when you click on PHeT, you're going to see two things, isotopes and mixtures. And you can, we're going to start with isotopes. It's actually a very quick activity. But what's really cool about PHeT, it allows you to drag and drop, and that can help with your understanding to really kind of get these ideas, understand them better when we can visualize them. So the ones that we're going to focus on, the elements we're going to focus on are hydrogen, carbon, and oxygen mainly. So what I'm after here is just that you're looking at dragging this neutron. We know that it is the proton, and that's what the pink thing is, orangey, pinky thing. This determines that it's hydrogen. This is a hydrogen 1. It has no neutrons, and then when we add a neutron, we know that the mass, well, yeah, um, I'll just refresh your memory that the atomic mass of the proton is very similar to the atomic mass of a neutron. They're the heavy particles. So now we have two, we could even click onto atomic mass, talking about atomic mass units, but I'm not concerned about that. I mean, you may be exposed to that in chemistry right now. We want to understand the stable, unstable idea when it relates to um, radioactivity and how we can use this concept for dating. Okay, so then I'm going to add another neutron, and look what happens. It becomes unstable. They animate this well. They show it, vibrating, because this is what um, they talked about in our content section, where we described the parent isotope. Whoops, sorry, the parent isotope, and then it's unstable. It releases. It's radioactive. We can pick that up and measure that, and then you have it'll become more stable isotope, which is called the daughter product. So here we have an unstable, so we know that this hydrogen 3, we could measure this radioactivity from hydrogen 3. And you're also going to learn later on that we can actually determine how long it takes for a hydrogen 3 to uh, change into a hydrogen 2 or a hydrogen 1, a more stable product. So there's things that you can click on here. Actually, no, it's not for the, I don't want you to do the abundance in nature, but you can flip around with the atomic mass or just leave it at mass number. So I want you to draw a picture of the, you can just do, what you can do is uh, do a stable hydrogen. Well, we know that hydrogen um, is hydrogen 1 is stable, just a proton. Hydrogen 2 is also stable. And then you can say hydrogen 3 is unstable. Okay, so you can do those three. Then I want you to move to carbon. And we're going to look at carbon 12. So we know that carbon 12, 6 protons, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, and 6 neutrons. You can see a little key up here as well. And I'm going to add a neutron. Does that make it unstable? Nope. It becomes carbon 13 because I now have 6 protons and 7 neutrons. So I want you to record that down. And it's still stable. What happens when I add another one? Now I get into my more unstable carbon. And this carbon 14 is the one that's used in a lot of dating. So it's unstable. It'll have a certain half-life. Again, we're going to talk about that, learn more about that very shortly. So I want you to draw those three pictures. There's a carbon 15, which is also unstable. Some of these are so unstable that we can't even find them existing on our planet. They so quickly um, break down and become a more stable isotope. So that's for carbon. And then for oxygen, again, this is not, we're just kind of practicing and getting familiar with what these isotopes look like. And these are just one atom that we're looking at. So oxygen is, we're going to do oxygen as well. So we've done hydrogen, carbon, oxygen, and we're going to add a neutron. Oh, it's still stable, but I want you to draw that one, oxygen 17. How many protons does it have? How many neutrons does it have? You don't have to do electrons. It's your call. It's really about this nucleus and the stability that is important for our dating. What happens if I add another neutron? Ah, this is still stable. This is interesting. Where in carbon, it became unstable when we added two neutrons. And now, when I get to oxygen 19, I get an unstable nucleus. Okay? And I want you to record this picture down. Okay? So that's just kind of to warm us up and look at the atom, individual atom, and what makes that nucleus stable and unstable. So then I want you to go down to the bottom here and click on mixtures. And for the mixtures one, this is more just a visual picture. I'd like you to still draw this picture. It will be very similar to the idea here and this one here, where I've done some particles and I'm showing half-life and two half-lives, but more about the half-lives. Actually, no, it's more about the percentage, the amount of stable and unstable isotopes or different types of isotopes that are naturally found in our um, in our world, our Earth, our atmosphere. Okay, water as well. So Nate, I want you to click on Nature's Mix for this one. So we're going to do the same thing. You can close this off if that's kind of busy. We're not really going to look at those because this picture is worth 1,000 words. So the purple is the hydrogen 1, which is stable. Um, we also knew the hydrogen 2 is stable as well. But you can see the quantity. There's most of the hydrogen is hydrogen 1, and then we can see a small percentage in nature that is um, hydrogen hydrogen 2. And so here they show, 99.9885% is that hydrogen 1. Okay? So I want you to very quickly sketch this picture, like with dots, or the idea is proportion that you're looking at. That if you look at a sample, because that's what you're going to be doing, you're looking at fossil samples or mineral samples, and you have to be thinking about particles, that they're made up of atoms, and some of these atoms, uh, actually, a lot of these atoms have isotopes. Some of them don't, but a lot of them have isotopes, and they are in different proportions that exist within a sample that naturally occur. Remember, this is in nature's mix. Okay, so I want you to do hydrogen, just quick sketch a picture. Color would really be helpful to draw that. I want you to also do carbon, and this is kind of interesting. We just see again two of the nature's mix again of the carbon 12 and the carbon 13. You can see there's um, a few more carbon 13s if I go to my percentage than there was with the hydrogen 1, hydrogen 2 comparison. And we can see again 98. The majority of the carbon is carbon 12. So I need you to know that, but also know that there's a small percentage. And you can use the numbers, but it's not required. But your picture needs to indicate that there's less carbon 13. Okay, and then I want you to also do oxygen. In oxygen, we can see that in nature's mix, there's actually the three types of isotopes that exist. Okay, and this is really, again, it's just visually, they've done a great job here. If oxygen 16 is the majority, if I wanted to click on my percentage, I can get numbers if that works better for you to see the numbers. But I can see that the oxygen 18, uh, uh, there's a very few amount. There's a few of the oxygen 18 isotopes, and then there's even fewer of the oxygen 17 isotopes. So really, that's all I wanted you to do for this exercise, just to start visualizing these particle pictures and the quantities that exist of these different types of isotopes. Okay, that's it.